So what are the subsets of it? So the subsets are C, D, and the empty set. Right, so if we start with C, what do we get? We get start with C as a we can derive, then we can derive A, and then we stop. Right, so we can't get to false. If we start with D, we start with D, we can derive D, we can derive B, and then we stop again. And if we start with the empty set, we can't get anything. Right, so no subset of it is, so it's a minimal conflict. Does that make sense? So the answer here is A. Questions? Yes? A superset of a minimal conflict is always it's always a conflict. That was the previous one, right? We had a superset of a minimal conflict. And we knew we could derive false from it. We didn't need to look at this. We knew we could derive false from it. And we knew because we already knew that E was a minimal conflict, so any superset of any superset of a conflict is a conflict, even. We've done that one. What about this one? Let's do this one. Same assumables, same knowledge base. Well, I'll look at C, D, E, and H. All right, anyone need more time? Stop. And hopefully everyone got this right. The answer is B. It's a conflict because it's got E in it. And it's a strict subset, so that was meant to be an easy question for people. And one that's maybe slightly trickier, but same assumables. But now A and D. Does anyone need more time? Does anyone still need more time? All right. Was it a wait? All right, we've got more people now, good. Okay, let's 3, 2, 1, stop. Trick question. The answer is D. I'll actually mark this because that was sort of a trick. This is actually meant for in a minute. Because we can only have, although we're proving these things, we can prove them with A and D. We're only sort of throwing assumables into our set. Okay, we're throwing into this set of these assumables. So we're not having arbitrary sets that imply false aren't allowed. The only conflicts are these assumables. Okay? That was sort of meant as a trick question, not to, so let's ignore that. All right. I think it's the last question. And now we're asking what's the set of all minimal conflicts? So remember, a conflict is a set, so we're asking for a set of sets. What's the set of all minimal conflicts? All right, does anyone need more time? 3, 2, 1, stop. All right, a few people said C. C is sort of an interesting answer because C, if you just sort of run through the, if you just sort of try and prove false and you try and collect up the assumables you get, sometimes you get E and D, sometimes you get C and E, sometimes you get C and D, and sometimes you get E, but E and D are not minimal because it's a subset. So C is not the right answer because E and D can't be a minimal subset because there is a smaller one that's also a conflict. And I thought more people might say A, but C and D isn't subsumed by E. The answer here is B. Okay, so we're not talking about counting in here. We're not talking about the number of them when we talk about minimal. We're talking about subsets. Okay, so the answer here is B. Any questions about that? Okay. All right. So today what we're going to do is we're going to end up talking about proof by contradiction, and then we're going to start talking a little bit about one of the dimensions we looked at was the dimension of not just features, but reasoning about objects and relationships amongst them. So we're going to start talking about that in order so that you know a little bit about one of the dimensions. And then later on next week, we're going to talk about planning. So that's where we're going to go in here. So we're going to talk about proof by contradiction. We're going to implement proof by contradiction. And then we're going to talk about individuals and relations and logical variables. But first of all, we're going to talk about conflicts for diagnosis. So the work that we're actually going to talk about here was stuff that was done by people essentially the theory of this was worked out by people at NASA and at Xerox, and this is sort of the basis for, there was a famous paper AI paper about diagnosis in Deep Space One, which is one of these things that's zooming out past Pluto. And this is the technology that's used inside there. And also apparently it's used inside photocopiers and all sorts of things, of making assumptions about how the world works, proving contradictions, then using that to troubleshoot what's wrong with these systems. So it's used on spacecraft and photocopiers, amongst other things. Okay. So we're going to use this example. So we're going to use this example, our running example of this light circuit. And the user is able to observe whether a light is lit or dark, and whether this power outlet is dead or alive. So whether there's power coming into the system or not. So let's assume we can observe that. And we're also going to have integrity constraints that says a light can't both be lit and dark, and an outlet can't be both live and dead. So we have all of these clauses like integrity constraints like false if light L1 is dark and it's lit. So if we claim it's dark and we claim it's lit at the same time, we get a contradiction. The same for L2 and the same for these power outlets, although that should be the same one. There seems to be a typo there. False if the one power outlet can't be both dead and live. And the other thing we're going to do is to make assumptions about individual components are working correctly. So we're going to start assuming that L1 is OK and L2 is OK. And for the moment, we're going to assume that all these switches are up. So here is my, So here's this picture. Let's put it on the other screen. Let's make sure I can start it. All right. Good. And we have, and this is my program that we the same as we had before. And now we've got this program. This is just the code we've been using before that's describing this scenario here. We just talk about whether the switch is alive, whether it's live outside. And now we're going to have assumables about whether these circuit breakers and switches are okay or not. Okay, and we also have in this thing, we also have mixing up askables, because assuming we have this very generic system that you can observe the world, we'd like to know what's going wrong. So this is, when we went through this before, remember, these up and down was something that the user could observe, but neither the user nor the system designer could observe okay directly. We're just going to start assuming it's okay and then proving by contradiction. So if we ask, what we're going to do is we're going to prove false. So I'm going to say, can we prove false? And it's going to, let's look at the bottom one, is L1 dark? And we're going to assume here the answer is yes. Otherwise it doesn't get very interesting. And we're going to make sure these two are up. So is S1 up true? We're going to do, is S2 up? And then we get this one contradiction, right, that says if we assume that CB1 is working okay, and we assume that light L1 is okay, and we assume switch 1 is okay, and we assume switch 2 is okay, then we get a contradiction. Okay, so if we look at these clauses here, that's sort of reasonably straightforward. We now have these rules, and in these rules, we just have assumptions of okayness. So we have this contradiction. Does that make sense? So assuming all of these facts, and we could do it the same way we did it here, but here we're just asking these queries, and now we have this set of contradictions. So this is a conflict. So let's write that down. So the one conflict is OK CB1, OK L1, OK S1, and OK S2. And now we could ask, is there any more proof you could do? So we can ask for more. Is down S1 true? The answer is no. Then we're going to ask, is L2 dark? Let's say it's yes. Is S3 up? The answer, I think, is yes. And now we're going to get another conflict. Assuming this, we're going to say it can't be the fact that OKCB1 or OKL2 and OKS3 are all okay. So if we assume the circuit breaker is working and the light switch is working and the light is going, we get a contradiction. Does that make sense what we're doing? Any questions about that? If we ask for more, we'll find there are no more answers in here. So what do you think might be going on here? What do you think might be wrong with our system? So we know one of these is wrong. We know that one of these is, essentially we know that essentially know that either not OK CB1 or not OK L1 or not OK S1 or not OK S2. Right, that's what this means. This is a conflict. It means this implies false, which means we know this. So knowledge base entails this. And it also entails not OK CB1 or not OK L2 or not OK S3. So is there any one thing that could account for all of these errors? For both errors? Is there any one thing that could account for all of these errors? Right, so these two have these two in common. So either we have, so this is equivalent to not okay CB1. So this and this. So we have both of these. True, right? Or there's a whole lot of double errors. So there's not okay L1 and not okay L2, or not okay L1 and not okay S3. There's a few more down there. Okay, so if we have this as our two cases, then either CB1 is broken, it's not okay, or we have a number of double errors, double faults. Right, so either we have a single fault, this is a single fault, or there's a whole lot of double faults. And what tends to happen in these situations is that it's unlikely that the two lights will burn out at the same time, right? Maybe it's unlikely that you'll have these double faults. So what people tend to do is they tend to look at these single faults and try to fix. It's probably the circuit breaker that's wrong. So let's try and fix that. Okay, so that's the way of thinking about this, right? So we either have, we know that this is true or this is true, so we're going to then look for these, whether they're single faults or double faults, or triple faults, or something else we need to assume. Any questions about that? Yes? Why does it care about switch S1? Because there's two proofs, there's two reasons why L1 could be lit, one of which is they're both up or one of which is they're both down. There are two proofs. If you look at here, it's very dumb this, right? It says there's two ways we can prove, what are we trying to prove? Lit W0, live W0. There are two ways of proving it. The first one is if S2 is up and live W0 is live W1. So it tries to prove live W1. Then it asks for is up S1. And the second way of proving it is it's trying to prove that maybe it's lit because they're both because S2 is down and S1 is down. It's trying to, essentially it's going through all the proofs. And it's just trying all the proofs, and so there's a number of proofs here of, and if you look at the proofs for false, right, the two proofs for false, and they're the two answers. Oh, we'll do it. Whoops, I messed it up. Okay, let's clear this. Let's load this up again. Because it remembers all my answers, right? And now it's. So what do you want me to say? Can you read that to make it bigger? I'll make it bigger. Is that better? Is that better? Good. So what should I answer? What do you want to say? So I can ask now, there's one answer, I can ask for more. Is down S1 true? You want to say yes? We actually had another proof, because we can go through the top wire or through the bottom wire. In this case here, there's actually the same assumptions in there. But it doesn't know anything. It doesn't know up and down are related. Right? It doesn't know these things. So you can keep asking yes. Right, we end up with repeated this one here because it switches both up and down. But we want to do that because there might be multiple reasons why it should be lit. And in systems like you have in NASA, you always have these redundant systems so that both of them effectively have to be broken for the engine to not work. So you want to, if it doesn't work, it's because both systems are down. Right, so we want to reason about these redundant systems. Any other questions? So this is what's on the slides. This is on what we did before. We can derive this. And they're the two examples, I think. So either CB1 is broken or is it one of 6 double faults. And so what we're going to do is we're going to define something called a consistency-based diagnosis as a set of assumables that has at least one element in each conflict. And so in here, and a minimal diagnosis is a diagnosis that's at no subset is also a diagnosis. And so if we look at these two, examples, one diagnosis is that OKCB1 because that has an element in both ones. So OKCB1 is a diagnosis. And another one is you have to have a set of, we need a set from an element from each of these. So you can have OKCB1 and OKL1, but that's not minimal. We can have OKL1 and OKL2. OKL1 and OKL2. OKL1 and OKS3. And right, so we can do this one with those two, we can do this one with these two, and this one with these two. We can do OK S1 and OK L2. And how many more are there? How many more are there? How many more of these are there?
Sorry, how exactly are you coming up with these sets?
Okay. I am choosing one element from this and one element from this, and I'm making so I can choose this, and I get this one. I can choose this and this, because I know you probably choose this and this because it's not, because I've already have one that has OKCB1. So nearly all of these cases, I don't want to choose bigger sets than I need to. I want minimal sets. So how many more are there? And how many more are there? Yeah, there are 3 more. Plus 3 more. Right, so there's this and these two. And there's this one and these two. There's all this, essentially the cross product, but we're removing non-minimal ones. So one way to think about it's a cross product of this with this as sets, but removing those ones that are not minimal. Because we either know in here that there's CB1 can be broken, it explains everything. Right? If CB1's not broken, we need two other things that could be broken. There's all these other combinations of things that could go wrong. Okay, any questions about that? So now we're going to talk about how to go about computing this. So this is the top-down consequent finding algorithm that we gave earlier, and that was in the exam, so everyone knows it. Everyone studied this one, right? So we select an atom, we choose a clause, we replace AI in the body with the body of C, and we keep going until we get an answer clause in here. And the algorithm with conflicts of finding contradictions is essentially the same as this. Let's go through here. The only difference is that the query we're going to do is now going to be false. We'd like to prove false, because what we're trying to do is to prove false. We're going to not select an assumable atom. When we're going to select an atom in here, in this thing we say we select an atom, and here we're not going to select an atom that's assumable. And we're going to stop when all the atoms in the answer clause are assumable, and this is going to be a conflict. Okay, and the other thing to do is, once we're doing this, in the middle of this, we're going to remove any conflict if a subset is also a conflict. So we can start pruning things, and we can also do this inside the algorithm. Okay, let's try and look at this example. So we're going to write yes. Oh, that's an awful pen. Yes, that's awful too. Yes, if false. So we're going to say yes, if A. And we're going to have A is true if B and C. Yes, if B and C. Now is B assumable? I can't read it. No, okay. Good. So I'm going to have two choices. I'm going to have two choices for B. I'm going to have the B if D clause, and I'm going to have the B if E clause. I didn't write the other ones in because there was only one choice. So with B if D, we're going to have yes if D and C. And I have to select an atom. Which atom should I select? Which atom should I select? Well, what's the rule? Now we have an extra rule. What's our rule? We don't select an atom that's assumable. So in here we have assumables at the bottom. D, F, G, and H. So what do I select? C. So I'm going to select C. And then I'm going to have C if F. Yes, if D and F. And yes, if D and G. And we have D and F. They're assumables. So we've got to here. And what do we know? What do we do here? What happens here? What do we do? Oh, what do the rules say? We just follow rules. We're just computers. We're dumb computers here. We're following algorithms. So when do we stop? So we don't select an assumable atom. They're all both assumable. We're going to stop. Right? So yes, if D and F, these are both assumable. So what do we know here? Right, so DF is a conflict. Let's write it here. So we know here that DF is a conflict. Right, so that's what I did. So back there, this is how the algorithm we saw worked. It just went down here and started. When we selected an atom, if it was askable, we assumed that if it was, otherwise we just collected it up. And now we're going to ask for a retry of this. We're going to say, is there another answer? Because we like all the conflicts, because we need all the conflicts to find the diagnoses. So yes, if D and G, then what do we do here? So D and G are both assumable, so so we have another conflict, right? So DG is a conflict. So we found two conflicts. Let's get going. B if E. So now B if E, we get a choice. What do we end up with? Yes, if E and C. Let's rub this off. So in here we're going to say yes if E and C. For select an atom, let's select E. We go to E if H and W. Or E is true if G. E is true if H and W. Well, we're going to select an atom. Which atom should we select? W. You have to select W, right? Then we got the rules for A. For W is F, so we get yes if F and C. Right, so now we're going to, let's move this up. Let's put this position 1. And we'll continue over here. At position 1, which is yes if F and C, now we're going to select an atom. What are we going to do here? We're going to select something. We're going to select C. And there are two rules for C, C if F and C if G. And now what are we going to end up with here? So yes if F and F. So what's the conflict? So what happens here? Sorry, what happens here? We found a conflict, right? What's the conflict? Does that make sense? But now we're going to do something interesting. Now I can, well, once we're here, if we know F by itself is a conflict, if we can actually prune this, because we know this has F there anyway, so you're only going to get a bigger conflict. Let's find a different color. So it turns out you can, we're not going to do this, you can prune this because it'll only be a superset. We can only find a superset of F. Right, and we can also prune this one, because now we can prune this one. That's what I said in here. You can take into account, remove any subset that's also, we can also take into account. So the algorithm I gave before is sort of pretty simple, but we can actually make it more sophisticated by pruning inside here. Once we get any set in here that's a superset of a conflict, we can prune it. And how are we going there? Oh, we might as well finish it now. So E of G, let's do position 2. Oh, let's do 2 over here. What is the clause? I can't see it. What's at position 2? Can someone read it out to me? Oh, this one here, this branch here. What's the answer? What should be at this branch here? Yes, if G and C. we still need C. Right, we now have two rules for G. Right, so we now have yes, if. So the two, we're going to select C. So the two rules for C, C if F. So we get yes if G and F. And then we get another conflict, don't we? This is another conflict. G and F. Can we prune that? Can we prune this? Sorry, we can prune this, right? Because we have a subset. Because it's a superset. And if we choose the other one, yes if C if G, we get yes if G and G. So we get a conflict of just G. And now we can start pruning other things. Right, we can now start pruning D and G. Does that make sense? So once we've found some conflict, we can prune any subset of it. And I think we've finished here. So what are the minimal conflicts here? So we're going to look through all these conflicts and just choose the minimal one. So this is G is minimal. So the minimal conflicts are just G. What else is there? Just F. Is D by itself a conflict? G, D and F is subsumed. D and G is subsumed. F and C is, sorry, that wasn't one, that was over here. F by itself is we have, and this one here. Does that make sense? So what we're doing is just proving them, collecting them up, and now we're going to get these conflicts. We're just going to check for minimality. This AI log system I give you doesn't check for minimality. It's really stupid, right? But it's trying to be like one of these car engines that you that has all the glass front so you can see how it works. Right? So it's trying to be very clear about what it's doing. All right. Any questions about this? Okay. So there'll be an assignment out that'll let you test and play with these things.